Welcome to the new lecture that is on recurrence relation. So here actually we will discuss about initially the basic concepts of the recurrence relations. So what is the recurrence relation? Actually we use here the series of numbers. What is the series of numbers? Suppose we have here the series is like that 1, 2, 3, 4, 5 and so on. So and suppose we have the series is like that 1, 4, 9, 16, 25, like that. So here the main thing is that for the series we have to find the what's the nth term of the series. So how can you find the nth term of the series if you have the series is like that 1, 2, 3, 4, 5? So here we say that suppose this is our the series is we denoted by S. So what is the nth term of this series? You can easily see that now the series are 1, 2, 3, 4, 5 and so on. So what's the you can easily identify here what is the nth term of this series. So the nth term of this series is Sn. We can say that this is n. So this is the nth term of this series. If we talk about this series 1, 4, 9, 16, 25 and suppose we say that this is denoted by t. So what's the nth term of this series? So here we see that the nth term of this series means Tn, that is n square, right? So after seeing this series you can easily identify that what is the nth term of these series, but it's not always possible. Means some series are like that you can't identify directly that what will be the nth term of that series. So what we do at that case, it is easy that to find the nth term that we use to find the nth term we use the earlier terms of that series. Like that suppose we have this type of series, we say that our x series are like that 3, 5, 7, 9, 11. So like that suppose we have the series. So what will be the nth term of this series? So we can say that is xn. This is equal to xn minus 1, xn minus 1 plus 2. So here we write the nth term of this series in terms of the previous term n minus 1. Nth term is xn, so we write this nth term xn in terms of the previous terms xn minus 1. So from this we can easily identify the series, but for this we need one more term that is called the initial term. So here our initial term x0 is 3. So if we have the initial term x0 is equal to 3, then we can find all terms of this series one by one. So first term is x0 is equal to 3, that is our the first term. And for the next term we use n equal to 1 here, means x1 what will be x1? So for x1 we put here x1 and we get x0 plus 2 and x0 is 3, so 3 plus 2 5, and like that we can find all terms of this series. So this form is the recurrence relation form. Means what is the recurrence relation? Where we can find our nth term in terms of the previous terms. So we can say that a formula which defines any term of a sequence in terms of any number of its previous terms or which expresses any term of a sequence as a function of its previous terms is called recursive, and the relation is called the recurrence relation. So when we express the nth term in terms of the previous terms, so this type of form is called the recurrence relation. And one more thing is that you all know about, familiar about the Fibonacci series. So what is the Fibonacci series? Fibonacci series is our what is that? So Fibonacci series is which type of that series is like that: elements 1 1 2 and 3 5 8 13 and so on. So what is the Fibonacci series? Fibonacci series is that where we get the next term, that is the sum of sum of two previous terms. 1 plus 1, that is 2, 2 plus 1 3, 3 plus 2 5. So we get the next term of the Fibonacci series, that will be the addition of the first two terms. So we can say that this is xn. Our nth term is the xn minus 1 plus xn minus 2. So we say that the nth term our is the addition of the two previous terms, and our initial terms here x0 is equal to 1 because our first term is 1, and the second term x1, that is equal to 1. So if you have the two initial terms, then you can find the Fibonacci series with this. So this is the recurrence relation of the series. But for the recurrence relation, what we need the nth, we can express the nth term in terms of the previous terms with the initial condition. We must need for this the initial condition. Without initial condition, we can't find the series from the recurrence relation. It's clear? Okay. So next is the order of the recurrence relation. So what's the order of the recurrence relation? Actually, the order of the recurrence relation is that if we can express the recurrence relation, the nth term of the recurrence relation in of the one previous term, immediately previous term, in terms of the previous terms, so that's the order of that recurrence relation is 1. Or suppose you can say that, suppose our series is like that, a equal to, we can say that 1 2 4 8 16 is like that. So what is the nth term of this? This is an equal to, what's the previous term? So in terms of previous term, how can we write the nth term of this series? That is an is equal to 2 times of, we can write this an minus 1. So an minus 1. So we write this an minus 1 because our first term, and we have to put here the initial term is a naught, that is equal to 1. So our first term is 1, and second term when we put here an equal to 1, so a1 is 2, a0 is our 1, so second term is 2, third term is now a2, that is 2, a3, that is 2, a2, that is 4. So we can write our recurrence relation an is equal to 2an minus 1 in terms of the one previous term. So for this we can write the recurrence relation is an equal to 2an minus 1. So here what's the order of this? The order of this relation is 1 because we write the nth term in the one previous terms, in terms of the one previous term. So that is the order of this relation. So you can say that the nth term in the sequence xn, such a relation xn plus 1 equal to fxn. One more thing is here that we can represent our the first terms or the recurrence relation in terms of an or an minus 1 or an plus 1 or an. both are the same. Means here the our nth term n term is depend on the n minus 1, and here is also our n plus 1 is depend on the is previous terms n. So we can represent our recurrence relation in terms of n or n minus 1 and n plus 1 or n. So like that, in example, xn plus 1 equal to 2 minus xn divided by 2. So here our the nth term, it's depend on the just previous terms xn. So xn plus 1 is equal to 2 minus xn by 2. So here what's the order of this? The order of this recurrence relation is 1, because here the final nth term is depend on the just one previous terms. So that's the order is 1. Or in generalized form, you can say that the order of the and the higher order is that we have also the higher order terms, higher order of the equations. That is, a recurrence relation can also be higher order, where the terms xn plus 1 could depend not only on the previous terms but also on earlier such terms like xn minus 1, xn minus 2, etc. So if our recurrence relation we can express is like that, xn plus 1, it is on depend on the two previous terms xn, xn minus 1. So we can say that the order of this recurrence relation is 2. This is the second order recurrence relation. Like an example, if we have that xn plus 1 equal to xn plus xn minus 1, so this recurrence relation has the order is 2, because here our the final nth term is depend on the previous two terms xn and xn minus 1. So the order of this recurrence relation is 2, and this is not other, this is the Fibonacci series, right? So actually, in the generalized form, you can also say that the order of the recurrence relation, we can identify the order of recurrence relation is the another way is that the difference between the highest and the lowest subscripts of the relation variable is called the order of the recurrence relation. Means also we can find out the order of the recurrence relation by the difference of the highest and the lowest subscripts. So like here we have the example is that 13 AR plus AR minus 1 is equal to 0. So what's the order here? Here you can see that the recurrence terms, that is AR, AR minus 1. So generally we see that our the AR is depend on the only the first previous terms AR minus 1. So we can say that the order of this is 1, and by the definition you can see that you can show that what's the order of this. So here what's the highest order, highest recurrence relation terms, that is R, and we have to take the difference, and the previous term is R minus 1. So when you solve this, so what you will get? You will get the 1, means the order of this recurrence relation is 1. Next one, we have this example 8fx plus 2fx plus 1 plus fx plus 2 is equal to kx. So what's the order of here? Here you can see that our terms, recurrence terms are fx, x plus 1 and x plus 2. So what's the order of this? The order of this is 2. Right, because here we have x, x plus 1, x plus 2. So our term is depend on the two previous terms. So the order is 2. Or you can calculate by the difference of this, the highest term is here x plus 2 minus the lowest recurrence relation, lowest subscript is x. So that is the order is 2. Clear? Next again we take the this example 3xn plus 2 plus 4xn plus 3xn is equal to 2. So what's the order here? Here our the recurrence terms are we have the three recurrence terms n plus 2, n plus 1, n. So we say that our recurrence term and nth term is depend on the two previous terms n or n plus 1 or n. So the order of this is 2. Clear how to find the order of the recurrence relation? So what's the order of the recurrence relation? If our recurrence relation nth term is depend on the previous two terms, so that is the order is 2. If depends on the previous one term, so the order is 1. So you can calculate the order of the recurrence relation. Now initial values, actually to generate sequence based on recurrence relation, one must start with some initial values. Earlier I told you that to find the recurrence relation, to series from the recurrence relation, we must need the initial values. Without initial values we can't find the series. So for the first order, this is our the first order recurrence relation xn plus 1 equal to fxn, because here our the last highest term is depend on the previous term xn. So to start with an initial value, so if we have the order is 1, if our recurrence relation order is 1, so we need the 1 initial value, okay, to find the series. And if our recurrence relation is of the second order, means our highest highest and term of the recurrence relation depend on the previous two terms, so we need to find the series, we need the two initial conditions x0 and x1. So if your recurrence relation is order 1, so you need the one initial condition to find the series. And if you have the two order recurrence relation, so you need to find the series, you need the two initial conditions. So like that, the higher order recurrence relations, we need the more initial conditions or initial values. Without initial values we can't find the series. Clear? You can check that if suppose our series, like we take the Fibonacci series, so here we have the what are the our recurrence relation, that is suppose we have that an, those, so that is are the an minus 1 plus an minus 2, right? So if we have the initial values, means a0 is equal to, we say that 1, and a1 is equal to 1, so we can find the our series, next term of the series. First value is a0 equal to 1, second is a1 equal to 1, so now the next value we can find a2 is 1 plus 1, that is 2. So without initial condition we can't find. Suppose I told you that you have not the initial conditions, right? So and I told you that find the, you have this recurrence relation and find the series. So can you find? No, you can't find the series of the recurrence relation, from the recurrence relation, without the initial condition. So you must have the initial conditions of the and the nth term of the with the previous terms for the recurrence relation. Clear? Okay, so now comes to the point, degree of the recurrence relation. So what is the degree of the recurrence relation? The highest power of recurrence term is called the degree of the recurrence relation. So we have to see here the highest power of the recurrence term. So let's see an example here. If we have this recurrence relation 3xn plus 2 plus 4xn plus 1 plus 3xn is equal to 2n. So what's the degree of this? What's the degree of this? You see that what's the recurrence term here? xn plus 2, xn plus 1 and xn. This is not the the recurrence terms, right? This is not the recurrence term. Our recurrence terms are only xn plus 2, xn plus 1 and xn. So what's the power this? Here the power is 1. So the degree of this is 1. Clear? So suppose we say that our recurrence relation is like that, 3xn plus 2 plus 4xn plus 1 plus 3xn, and I say that this is equal to 2n square. So what will be the degree here? Here we have to consider only the recurrence term, and our recurrence terms are here and xn plus 2, xn plus 1 and xn. So the degree of this recurrence relation is again the 1 because it is not the recurrence term. Clear? Now another example, if we have suppose yk plus 2 cube plus 2 yk plus 2 plus minus yk is equal to 0. So what's the degree here? Here we see that our recurrence terms are yk plus 2, yk plus 1 and yk, and the highest power of the is here 3. So the degree of this is 3. Now another example, AR4 plus 2AR minus 1 3 plus 2AR minus 2 and 4AR minus 3 equal to 0. So what's the degree of here? Can you tell me what's the degree? Here we are, the recurrence terms are AR minus 1, AR minus 2 and AR minus 3, and the highest power is 4. So we say that the degree of this is 4. Clear how to calculate identify the degree of the recurrence relation? And if our recurrence relation has a degree 1, so that is called the linear recurrence relation. And in this our study we will discuss about and we will study about only the linear recurrence relation. Now let's take some examples here about the recurrence relation. Suppose you have given this recurrence relation ak equal to 2ak minus 1 plus k for all integers k is greater than equal to 2, and the initial condition is given that a1 equal to 1. So here you have to find the first 4 terms of this recurrence relation. So here we calculate the first 4 terms. So our first term is given that is a1 equal to 1, it is given. So now what will be the next term? That is here is given that k is greater than equal to 2, so we can take that k is equal to 2. So put here k equal to 2, so we get 2 and k minus 1, our k is 2, so this is 2 minus 1, so this is 2a1 plus k we take here the 2, so 2. So we can calculate the second term, 2a1. a1 is our the 1, so that is 2 multiply 1 plus 2, so that is 2 plus 2, that is 4. So our the second term of this recurrence relation is 4. Now similarly you can find the next term, that is our the third term, a3. So what will be the a3? This is 2 and a3 minus 1, so this is a2 plus k is 3 here, so 3. So put here what was our a2 is 4, so you put here 2 multiply 4 plus 3, so that will give you 2 for 8 plus 3, so 8 plus 3 you will get the 11. Now we have to calculate the fourth term, so the next term is your fourth term, that is a4. So a4, when you put here k equal to 4, so you will get a, and 4 minus 1, that is 3, so 2a3 plus 4. So now what is your a3 is, you have calculated that is 11 plus 4, so that will give you 26. So like that you can find the all terms, but here we need to find only the first 4 terms, so that are 1 your first 4 terms are 1 4 11 and 26. Clear? So like that you have to find the terms. Another example, here also we need to find the 4 terms of this recurrence relation, that is ak minus 1 plus 3k minus 2, and here 2 initial conditions are given. Why 2 initial conditions are given? Because here our the kth term is depend on the k minus 1th and k minus 2th term, first 2 previous terms. In terms kth term is depend on the k minus 1th term and k minus 2th term. So here we need to find the terms, we need the 2 initial conditions. So here a0 and a1 is given, so already we have the first 2 terms are a0 is 1 and a1 is given that 2. So we need the first 4 terms. So what will be our the next term? So our next term is a2, So we calculate here a2, put k equal to 2, so that is 2 minus 1, that is 1. So plus 3 and a2, so this is a0, and we know the value of a0 and a1. What is a1? That is 2, plus, and what is a0? That is 1. So you will get the 5. 2 plus 3, 5. So our the third term is 5. Now the fourth term means we have to calculate here the a3 is the fourth term. Put here k equal to 3, so that is 3 minus 1, that is 2, plus 3, a3 minus 2, that is a1. So now put here the value of a2 is 5 plus 3, and the value of a1, that is 2. So you will get 5 plus 6, that is 11. So like that you have the first 4 terms of this recurrence relation is 1, 2, 5 and 11. Clear? So now here we have the another example. Here we have to show that this sequence 2, 3, 4, 5 plus 2 plus n, for n is greater than equal to 0, satisfy the recurrence relation ak is equal to 2ak minus 1 minus ak minus 2, where k is greater than equal to 2. So here we do this question some different way. So here you have this sequence. So what is the nth term of this sequence? So here the nth term of this sequence an is, this is 2 plus n, right? So this is the nth term of this sequence, 2 plus n, and our the recurrence relation is given in terms of the k, that is ak is 2ak minus 1 minus ak minus 2. So what is our the kth term here? In terms of kth we can write this ak is the 2 plus k. So this is our the ak. So we have to actually verify this, the recurrence relation with this sequence. So we have this ak is equal to 2 plus k. So we can solve this as by, we can put here in place of k minus 1, and in place of k minus 2, and put here and find show that both are equal. The left side is equal to the right side. So we can put here, suppose k minus 1. So if we put k minus 1 in place of k, so what is this? This is 2 plus and k minus 1. So what you will have now? This become 2 plus k minus 1. So yes, this is, you will give the k plus 1, right? You will get k plus 1. Now when you put here k minus, oh sorry, because this is ak, this is equal to 2 plus k, and you have the given is ak equal to 2ak minus 1 minus 2, yes, this. So now what will be the ak minus 2? So when you put here k minus 2, so you will get 2 plus, and in place of k you put here k minus 2, so it become k. So now put here in this recurrence relation both sides the values, these values in both sides, and you verify that left hand side equal to right hand side, so you can verify that this is right recurrence relation. So what is your left side? That is ak, and ak is 2 plus k. So now put here the value in right side, so that is 2 ak minus 1, and what is ak minus 1? This is your k plus 1, and minus ak minus 2, so ak minus 2 is your k. So you solve this, this become 2k plus 2 minus k, so it become k plus 2. So 2 plus k, this is k plus 2, you can write it 2 plus k, so both are equal. So we can say that this is the correct recurrence relation of the sequence. Okay, so now come to the coefficients. Actually constant coefficients means that if your recurrence relation, what are the coefficients here? 2, 1, 3. So all, you can see that all the coefficients here are the constant values, 2, 1, 3. So this is, if you have the all values, all coefficients are constant of your recurrence terms, so you can say that this is the recurrence relation, with the constant coefficients. And if your terms, your recurrence relation coefficient, here is 2, here is k, here is k square, so these are not the constant, so this is called the non-constant coefficients. So you can say that this is the recurrence relation with non-coefficient constant coefficients, right? So you have to consider the recurrence terms coefficients. If these are constant, so this is the constant coefficients recurrence relation, and if your are the non-constants, the variables, so you say that this is the recurrence relation with non-constant coefficients. Now come to the homogeneous and the non-homogeneous recurrence relation. So what is that? So here, if we represent the recurrence part in terms of Fn, so like that, this is the your recurrence relation is ak plus 2 a3 ak plus 1 2 minus 3 ak. So here your recurrence term k plus 1 k plus 2 k plus 1 and ak, so we represent it, suppose this part, recurrence term part, by fk, right? So here, if your this expression, this fn is equal to 0, so you say that this is the homogeneous recurrence relation, and if this part is not equal to 0, so we can say that this is the non-homogeneous recurrence relation. So here, if we talk about this recurrence relation, here our fk, this is equal to 0, so we say that this is the homogeneous recurrence relation. This is the homogeneous recurrence relation, right? And here you see that these are the recurrence terms n minus 1 n minus 2, sorry, this is the actually a. So an minus 1 an minus 2 is equal to 2n. So this is our fn, but here fn is not equal to 0, so here fn is, you say that this is not equal to 0, so this is the non-homogeneous recurrence relation. This is the non-homogeneous recurrence relation. Clear? Now here we have the we take some examples here, and here you have to find the order, the degree, and the homogeneous or non-homogeneous, and the constant or non-constant coefficients. So here our first example is that ak recurrence relation is that ak is equal to ak minus 1 plus 3, and the initial condition is given a0 equal to 1. So first you tell me what's the order of this recurrence relation. So here you can see that the kth term is depend on the only the first previous terms, k minus 1th term. So the order of this is, this recurrence relation is of the first order. The recurrence relation is the order is 1. So the first order term, and this, because this the coefficient is 1, this coefficient is 1, so all the constant coefficient terms of the recurrence relation, so this is the constant coefficients recurrence relation. This is the recurrence relation of the constant coefficients, right? And next one is that this is the homogeneous or non-homogeneous, because our the recurrence part is this ak minus 1 plus 3, so this is the non-homogeneous terms, because here this is not equal to 0 fk. If you say that what is your fk here, this is your ak minus 1, right? And this is not equal to 0, this is equal to 3, so you say that this is the non-homogeneous recurrence relation. This is the non-homogeneous recurrence relation, right? And this is the what is the degree of this is 1, so we say that this is the linear recurrence relation. Clear? Okay, so now next one is bn equal to n bn minus 1. So this order is, this is only depend on the first previous term, so the order is the one of this is the first order recurrence relation. This is the first order recurrence relation, and this is the homogeneous or non-homogeneous. Yes, you can write this bn minus n bn minus 1 is equal to 0. So the fn is equal to 0. So this is our the homogeneous recurrence relation. Clear? Next one is it is linear. Yes, because the degree is 1, so this is the linear recurrence relation, and this is the constant coefficient or non-constant coefficient, because the coefficient of the recurrence term is n here, so this is the non-constant coefficients here, right? This is the non-constant coefficients. Now come to the here fn equal to fn minus 1 plus fn minus 2. So what's the degree, sorry, what's the order of this recurrence relation? Because here the nth term depend on the n minus 1th and n minus 2th term, two previous terms. So this the order is this second. So this is the second order recurrence relation. And this is the homogeneous or non-homogeneous? This is the homogeneous, right? Because fn equal to 0 here, so this is the homogeneous recurrence relation. And this is linear or non-linear, because here the recurrence terms highest power is 1, so this is the linear recurrence relation. And constant or non-constant coefficients, because coefficients are on 1, so this is the constant coefficients recurrence relations. Constant coefficients recurrence relation. Okay, so now you can identify what's the order and what's the degree, and those coefficients are homogeneous or non-homogeneous. It's clear? Okay, so these are the actually basic terms of the recurrence relations. So now in the next lectures we will discuss about the solution of the recurrence relations, how to solve the recurrence relations. So today's lecture is completed now. Thank you. Be happy.